Welcome to Lesson 4. One of the reasons many people dislike math and don't do well is the messages they have in their heads. The other is that they're not introduced to math in the right way, and they get the idea that math is something it's not. And this turns out to be very important for learning. Many people have been led to believe that math is a lot of methods and rules that have to be remembered. An individual subject best learned alone with a book or a teacher. All about right and wrong answers, not interpretation. It has no opportunities for creativity and is about being fast with numbers.
All of these ideas are wrong!
In this session, we're going to focus on numbers because they're the basis for all higher level math, and we know that what separates high achievers from low achievers is not that the high achievers know more math, it's that they interact with numbers flexibly and low achievers don't.
What does this mean? Let's try something together.
I want you now to work out 18 times 5. In your head with no writing on paper, just trying it in your head. It doesn't matter if you're wrong, that will help your brain grow.
The answer is 90, but don't worry if you didn't get that, as that means synapses are firing. The most interesting part of the problem is not the 90, it is the ways people get to 90, the different pathways they use.
Do you remember those interviews in San Francisco that we showed you in the first lesson? Well, we also asked the people to work out 18 times 5. We asked some Stanford students too. What was striking is that people work out the problem in so many different ways.
First I'd do 10 times 5, 50, 8 times 5 is 40, so 50 plus 40 is 90.
Okay, thank you.
18 times 5, well, the easy way would be 10 times 5 and then 8 times 5 and then add those together. 90, right? Yeah.
Okay, thank you.
I just times the 5 times the 10 and then multiply the 5 times the 8, get 90.
Okay, cool. Right.
Okay, well, I would probably go up to 5 times 20 first, be 100, and then just subtract, I guess, 10, right? So 90.
Okay, awesome, thank you.
Okay.
I feel like I should be able to answer 18 times 5 pretty quickly, but I can't. It takes a while. I do know it's 90. I think I'd probably do it with the 18 on top and then the 5 on the bottom and then 5 times 8 and 5 times 1 and then add it together. It's probably a pretty slow way of doing it.
That would be 90.
Okay, and how did you get 90?
Well, first I doubled 18, getting 36, then I doubled that, getting 72, and then I added 18 again, so
okay,
that was my
90.
And how did you do that?
So I take 18 and I have that. 9 times 5, 45. 9 times 5, 45. Add them together, 90.
18 times 5 is 80.
How'd you get 80?
5 times 10 plus 5 times 8. No, 90.
90.
And can you just describe your method of how you got to that?
I did 9 times 10 instead of 18 times 5, because same thing.
Awesome.
We can also see the strategies visually in these ways. So some people said they didn't want to multiply 18 times 5, they wanted to multiply 10 times 5, and they got 50, and 8 times 5, and they got 40, and then they added those to get 90. So what would that look like visually? Well, if we draw our 18 times 5 and say that looks something like this, what they were doing was they were saying they didn't want to multiply 18, so instead they multiplied 10 by 5 and 8 by 5. And that's how they got their 50 and their 40. But some people, they said they didn't want to multiply 18 times 5, so instead they multiplied 20 times 5, which gave them 100. And then they subtracted 2 times 5, which is 10. And they got 90. What would that look like visually? Well, let's imagine this is our 18 times 5 again. And they said, well, I don't want to work with 18, I want to work with 20. So they made their 18 into a 20 by adding 2 on. And then they subtracted that and took it off. So that would look something like that visually. Some people said, instead of multiplying 18 times 5, they said, I'm going to multiply 18 times 2, and I get 36. And then there were 2 sets of those, which give me 72, and then I add my last 18, which gives me 90. And visually, what they were doing was they were saying, here's my 18 times 5, and I want to multiply 18 by 2, 18 by 2, and 18 by 1. So that's what that would look like visually. And then one of the others, I think my favourite method of 18 times 5, is people who said, well, 18 times 5 is really the same as 9 times 10. So what would that look like visually? Let's think, if our 18 times 5 looks something like that, those people were saying, I'm going to work with 9, and then I need to double this and make it 10. And they worked out that area instead. So those are 4 different visual solutions from some of the different methods we heard. We just showed you the visuals for the strategies people used. Now see if you can match each visual to each strategy. Some people think that you can't or shouldn't change numbers in the ways we watched, working with a 20 instead of an 18, for example. They think that you're somehow not allowed, but it turns out to be a really important thing to do.
Some people think there's only one way to solve a problem, or they think that the only way to solve a problem is to use an algorithm, like in multiplication when you put one number on top of the other and multiply each number step by step. And often that doesn't make sense to people.
People see mathematics in very different ways, and they can be very creative in solving problems. It is important to keep math creativity alive. If you ask mathematicians what math is, most of them will talk about a beautiful, creative subject, but often the beauty and creativity isn't seen in school math.
When you learn math in school, if a teacher shows you a method, think to yourself, what are the other ways of solving this? There are always others, and discuss them with your teacher or your friends or parents. This will help you learn deeply. I'd now like to give you another opportunity to use numbers flexibly. Try this problem, and this time don't use an algorithm, if you did before, where you write them out and you carry numbers, but try changing the numbers into friendlier numbers, as we saw in the videos. And the problem is 12 times 15. So number flexibility is really important. Another thing that's really important, both in being a powerful math communicator and in understanding more deeply, is to engage in something that's called mathematical reasoning.
A lot of people think of math as an individual solitary activity, but collaborating, talking about math, is really important in your learning of math, and it is the way math is used in most companies in the world, as we will see later.
When you talk about math, you have access to a different level of understanding than when you just read questions or work through them on your own.
An important mathematician called Yuri Treisman found that large groups of students were failing Berkeley calculus classes and leaving the university. So he studied the students who were failing and those who were not.
His results were stunning. He found that those who did well did not have higher grades coming to Berkeley. They did not know more math. They did not come from more wealthy backgrounds. There is one difference between the successful and the unsuccessful students.
The unsuccessful students worked on math alone. The successful students talked about the math they were given in class. They worked on math as they ate dinner at night, or they met in groups to work on problems together. So Treisman started study groups for the students who were failing, where they sat and worked on math problems together.
The results were dramatic. Within a year, the students who were failing, but then worked in study groups, started outperforming the other students. Many of the students who were in those workshops went on to become scientists, engineers, and even Rhodes Scholars.
Why do you think that the students who worked on math together did so well in their math class afterwards? Talking gives access to understanding. It's really, really helpful for understanding math. But it also does something else.
When you talk, you do something really important in math, which is called reasoning. Reasoning is when you talk through your methods and give reasons for your choices. This is really the essence of what mathematics is.
When you work on a math problem, if you can think about the pathways you're taking and tell someone else, and then discuss the choice of pathways, you're doing something really important.
This is what mathematicians do for their job. They discuss their reasons for the pathways they take with other mathematicians. And often great breakthroughs are made in maths because someone gives a result, and even though their result was wrong, they formed a pathway that others then use to make great breakthroughs.
Reasoning is also super important for working in today's technological world. In high-tech companies such as Google and Facebook, everyone uses math. But they use it by having an idea, mapping out a pathway, and talking to others about it. They connect with each other's thinking to create things. The math is totally collaborative and usually very creative. We will come back to that idea in the last lesson.
Soon, most jobs will need math work. Lots of companies now have huge data sets, and they need people to ask questions of the data, talk about it, use math to gain insights.
So talking about math reasoning is really important. It helps you understand math, and it will prepare you for math in the world and in work.
If you chose all three, give yourself a pat on the back because all three are true. Reasoning is really important for jobs. It allows people to connect ideas and make mathematical breakthroughs, and it's the essence of what mathematics is. Scientists prove theories by testing lots of cases, but mathematicians propose ideas and use reasons to show that they're mathematically true. We've seen the importance of number flexibility and reasoning talking about math. The third idea we want to show you today is about mathematical connections. It turns out that people who do well in math are those who make connections and see math as a connected subject. People who don't do well are the people who see math as a lot of isolated methods. So we're going to take you on a mathematical tour now to illustrate what we mean by this. Don't worry about following all the math if it's new to you. This isn't to teach you math, it's to show you how it's connected. Try to follow along though, there's some exciting ideas in here. So some fractions are equivalent. Here are three of them. They're called equivalent because they have the same relationship. As you can see, the fractions cover the same area on the same size rectangle. Fractions can also be shown on an xy coordinate graph. This graph shows us the relationship between the numerator and denominator. It also shows us three similar triangles, as you can see. Our journey now takes us to an area of math where shapes transform, where they become bigger, smaller, or when they move position. So we can take our 3, 4 right-angled triangle, which we'll draw again here, and dilate it by a scale factor of 2. This means that every side is doubled in length. We multiply each one by 2. That gives us a different triangle, and in fact it gives us our 6, 8 right-angled triangle. We can then take that triangle and perform another times 2 dilation to get our 12, 16 right-angled triangle. Or we could have dilated our 3, 4 right triangle by a scale factor of 4, and that would also give us the 12, 16 right-angled triangle. We'll show you that. That's part of the fun of transformational geometry. Our triangles and fractions are also connected to the big topic of rate. Rate is a special kind of fraction or ratio where different units are used. For example, you might have miles per hour. When we graph our 3 points, we can draw a line, and every point on the line has the same relationship, or rate, and that rate is always 3 to 4. We're now going to journey into the world of algebra, where we're going to find Mia studying a cheetah. Mia's interested in how far they run, and she finds that this cheetah runs at this rate. So Mia graphs the rate, and you can see in 3 minutes the cheetah runs 4 miles. In 6 minutes they run 8 miles, and in 12 minutes she runs 16 miles. And now she can write an algebraic expression for the rate, y equals 4/3 x. But now she's pondering. Something to think about here and to talk about. Why do you think it's y equals 4/3 x and not, for example, y equals 3/4x? Something to think about. So to find the slope of that line, we can draw another triangle, and that helps us find slope. So there's a cheetah, and some people call this a slope triangle. Another cool thing, our numbers that we chose for you are Pythagorean triples. Pythagoras lived in Greece, and he noticed something really amazing, that when we have a right-angled triangle, here's a picture from Greece, the areas of the two squares on the two sides of the triangle add up to the area of the square on the hypotenuse. Always with any right-angled triangle. Pythagoras' theorem is often expressed as a squared plus b squared equals c squared. And here you can see how that works. The squares on the two sides of the triangle make the same area as the squares on the hypotenuse. So Pythagorean triples are right triangles in which the length of the two sides and the length of the hypotenuse are all whole numbers. So 3, 4, and 5 are called Pythagorean triples. So, in fact, 6, 8, and 10, 12, 16, and 20. So we've taken you through this mathematical tour to illustrate something. In just a few minutes, we've journeyed from number to geometry to algebra, then back to geometry and number. About 8 years of school, but all the ideas we've shown you are linked to one idea, mathematical proportions. So all of these things are expressing a proportion or a relationship. So here are some of the paths we've travelled in this tour. We've made a little concept map, and it shows you all these areas of mathematics. And when we thought about proportional relationships, we started off with fractions, we made a table, we drew graphs, we then took it into geometry and transformational geometry. We looked at dilation, then we talked about algebra, and we thought about slope. But all of these things are connected to one idea. So math is a subject of beautiful connections. It's not a long list of disconnected topics, even though it may look like that from the books you've had to work through. Never give up looking for mathematical connections. They will really help you. Mathematical connections are really important to the subject and to you.
Every 4 years, the PISA team conducts international surveys and tests to find out how students think about math and how well they achieve in math. In the last survey, they found this.
The lowest achieving students were those who used a memorization strategy. When they approached math, the lower achieving students tried to remember lots of methods. When they studied for a test, they tried to memorize methods by heart. The highest achieving students were those who approached math by thinking about big ideas, thinking about what they knew and didn't know, and thinking about how math related to the world. This is a different approach that is more about big ideas and connections.
The highest achieving students of all were those who had a growth mindset and used thinking math strategies of thinking about the big ideas and connections. those students with the most powerful beliefs about themselves and learning and the best math strategies to use were the highest achieving students in the world. And this graph shows you the PISA results from 13 million 15-year-olds in 34 countries. What this shows us is that students with a fixed mindset who believed you're good at math or you aren't were the kids who achieved at the lower levels. And the kids with a growth mindset were the highest achieving. And kids with a growth mindset who also used positive strategies, who made connections and didn't memorize, were the highest achieving students in the world. In this session, we've learned about number flexibility, talking and reasoning, and mathematical connections. Now I'd like you to write about some of these important ideas to someone of your own age. Explain to them why they're important for their learning in a paragraph now.